Jai Hind students, welcome to my YouTube channel. Students, the way you think and feel about yourself, including your beliefs and expectations about what is possible for you, determines everything that happens to you. So it all depends on your thinking, right? So when you change the quality of your thinking, you change the quality of your life, and that too sometimes instantly. So just as positive words can make someone smile or a well-timed humorous quote can make someone laugh, our thoughts actually react to the world in real time. So students, you have complete control over only one thing in the universe, and that one thing which you have complete control is your thinking. So always think positive. Always have that positive approach towards life. Right? So with that students, let's begin today's session. Continuing with the previous article, today we will be discussing the bending of a cyclist. Now students, whenever a cyclist or a motorist makes a circular turn, then he tends to bend himself with respect to the vertical through some angle so as to execute the circular turn. Right? We are aware students, force of friction does play a role, right, in offering necessary centripetal force in making the body to move along circular path or in making the vehicle to execute a circular turn. But force of friction is an unreliable force because it depends upon the nature of the surfaces in contact. As I have told you, in case of wet surface or in case of road surface in which some oil is spilled, then the friction gets greatly reduced. So as a result, we can say or we can conclude safely that force of friction is unreliable force, and it offers or it rather contributes very small towards the centripetal force. So that is why bending of a cyclist is necessary. By bending, what happens is a component of the normal reaction force that acts in the radially inward direction. So that component along with the friction that provides the cyclist or the motorist the necessary centripetal force so as to enable it to execute the circular turn. So this is what we are going to discuss, right? So we are dealing with this topic of bending of a cyclist. So suppose friends, this is a turn, this is a circular turn and this is a cycle. I have not drawn the cyclist obviously, right? So this is the vertical. So while taking the circular turn, he cannot remain upright, right? He has to bend. Remaining upright, in that case, the weight of the cycle along with the cyclist will get balanced by the normal reaction, and force of friction being not so large, it can't provide that necessary centripetal force, and also force of friction being not reliable. So in such a case, bending is must while taking a circular turn, right? So let me verify this fact mathematically. Suppose this is the center of the mass, where the entire mass of the cycle along with the person who is driving it is assumed to be concentrated, right? So the total mass of the system is suppose capital M. So obviously weight will act in the vertically downward direction and it is mg. Remember students, M is the mass of the cycle plus the cyclist. So M is the total mass of the system, right? And let us consider the cyclist to bend at an angle theta with respect to this vertical. This dotted line represents vertical, right? So as a result, now what happens is the ground will exert a normal reaction force to the cyclist, right? So this will be the reaction force. It is perpendicular to this. So it will be like this. This is the reaction force. Clear students? Now reaction force, we will try to resolve it into two perpendicular components. One in a direction opposite to mg, that is along the vertical direction. So this is the transversal and these are the two parallel lines. Therefore, this angle would be equal to this angle, pair of corresponding angles. Am I clear, students? So the component of R along the vertical direction opposite to the direction of the weight is R cos theta. This component of the reaction R cos theta, as it's pretty evident from the diagram, will balance the weight of the system, which is the weight of the cycle and the cyclist, right? The other component, which is R sin theta. The other component is R sin theta. It will act, or rather it acts along the radius towards the center of the circular track or the circular turn, right? So whenever the force acts in the radially inward direction, the nature of that force is centripetal. It makes the body to change its direction of motion continuously, right? So R sin theta being directed in the radially inward direction, it will provide the cyclist the necessary centripetal force. And here I am considering the force of friction with the tire and the road surface to be negligible, as it is unreliable, so I will try to ignore it. So shear bending of the cyclist will provide this component of the reaction force R sin theta, which will act in the radially inward direction. That is, it will act along the radius towards the center of the circular turn. And thus, this component of the reaction will provide the cyclist the necessary centripetal force. Right? So, mathematically, students, R sin theta, it would be equal to centripetal force, mv square by r. V is the speed of the cyclist at the instant when he is taking the circular turn, right? R is the radius of the circular turn under consideration. Also, as I told you, the component of the reaction force R cos theta, that will balance the weight of the cyclist, right? So, dividing these two, what do you get? First divided by second. So, sin theta by cos theta, that will give you tan theta. R will get cancelled. Here mm will get cancelled, so we get v square divided by r. So students, this is the angle. Theta is the angle which the cyclist must bend with respect to the vertical so as to execute the circular turn. Right? V is the velocity of the cyclist at that instant, R is the radius of the circular turn, and G obviously is the acceleration due to gravity. So the angle through which the cyclist needs to bend with respect to the vertical is theta is equal to tan inverse V square divided by RG. Right, students? Okay, students. Now next we will consider the motion of a body in a vertical circle. Like, let us consider a string of radius r and hold its end through your hand, and the other end be tied to a stone or a ball, right? And the body is made to whirl in a vertical circular loop like this. The body is made to move along a circular path in the vertical plane. So that is known as vertical circular loop. In order a body to execute vertical circular loop, there must be a minimum velocity of projection at the lowermost point, right? So that is what we are going to discuss in this particular episode, right? So in this lecture, in this topic, we are going to discuss the expression for the tension in this string, right? Then we are going to find out the expression for the minimum velocity of projection at the lowest point, and then we are also going to find out the expression for the velocity at the highest point. So we are talking about vertical circular loop. This is a circular loop which is executed in a vertical plane. Clear? So students, this is suppose the center and this is a vertical circular loop. This is a body, say of mass m. This is obviously the lowest point. As the body is made to execute the vertical circular loop, then what happens? As it goes up, obviously its velocity will keep on decreasing. At the highest point, this is suppose the highest point, its velocity will be minimum. This is suppose the highest point, right? So let us consider the body to be made to execute the vertical circular loop in the anti-clockwise direction, like this, in the anti-clockwise direction. Clear? So, at this instant, which is the lowest point, the velocity must be maximum. This is the velocity of projection. Let us denote it by VL. This is VL. This is the velocity of projection, right? At the highest point, as I've told you, as it gains height, its potential energy will increase and kinetic energy will decrease. And as per the law of conservation of energy, the sum of kinetic energy and potential energy must remain constant, isn't it? At any instant during the motion of this body, the total energy possessed by the body at any instant should always remain constant. So, as the body moves from lowest point to the highest point, due to the gain in height, it will lose its velocity. So here the velocity would be minimum. So suppose the velocity at the highest point will be given by VH, right? It's been represented by an arrow of smaller length. And let us consider, students, this to be an arbitrary point. So the body is going like this. So at any instant when the body follows a third path, the direction of motion at a point is given by drawing a tangent at that particular point, right? So at this point, its direction of motion will be given like this. So this is V. Obviously, this V is greater than VH but less than VL, right? As it gains height, its velocity will keep on decreasing and it will keep on gaining in height. So, this is the center and this is the string. We have considered this to be of length R, right? This is a string of length R. Clear, students? And let us consider the angle which the string makes to the vertical. Suppose let it be theta. This is any arbitrary point. Suppose this is point A. This is any arbitrary point A. Right, students? And let us consider this to be the reference line. This is suppose the reference line. So obviously VL is maximum. V would be less than VL. V is the velocity of the body executing vertical circular loop at any arbitrary point A. And at the highest point, the velocity of the body will be minimum. Right? So do remember this. Okay. Now what we do is, let's apply the law of conservation of energy. We know that at any instant during the motion of this body, the total energy must remain constant. So, let's apply law of conservation of energy. Law of conservation of energy, which states that energy can neither be created nor it can be destroyed. The total energy possessed by a body always remain constant. Therefore, total energy of this body executing this vertical circular loop at point L, at the lowest point, it should be equal to the total energy possessed by the body at point A, isn't it? At any point, the total energy must remain constant. So, at point L, this is the reference line. So, from this reference line, the height of this body is 0. So, potential energy with respect to this reference line would be also 0, right? So, at the lowest point, the body will possess only kinetic energy. So, it may be represented like this. I'll substitute the value of kinetic energy and potential energy later on. So, this is kinetic energy at point A plus potential energy at point A. Right. Kinetic energy at point L, it is half mVL square. Expression for the kinetic energy, we all are aware, it's half mv square, right? Plus potential energy, its expression is mgh. So here, the height with respect to this reference line is 0. So potential energy would be 0. Kinetic energy at point A, its velocity is v, so it will be half mv square plus potential energy at point A. At this point, it has gained this height. Suppose it gets raised to height h, right? So here it will be mgh. h. Am I clear, students? So if you rearrange the terms and in both the sides get cancelled, so we get VL square multiplied by 2 on both the sides, we get V square plus 2GH. Or students, V square it is equal to VL square minus 2GH. Put this as equation number 1. We'll be using it very often, right? So I'll write it over here. V square, the velocity of the body at any instant during the execution of the vertical circle loop is given by V square is equal to VL square minus 2GH. So put this as equation number 1. Clear, students? Now let's draw the vector diagram. Right? What are the forces acting on this body? One is, students, obviously it's weight. Weight will act in the vertically downward direction. It is mg. The other one is the tension. Tension will always act along this string towards the point of suspension. Tension is a force which acts along the length of the string towards the point of suspension. Right? So here what we do is, we can resolve mg into two perpendicular components. One in the radially outward direction like this. This is the radially outward direction. One along this direction. Now look, students, this is theta. These are the two lines which are parallel to each other. This line will act as a transversal. So this angle would be equal to this angle. This is also theta. So mg can be resolved into two components. This component in the radially outward direction is mg cos theta, while the other component, tangential, it would be mg sin theta. This component is mg sin theta. So what we have done is, we have resolved mg into two perpendicular components. Mg cos theta in the radially outward direction, mg sin theta in the tangential direction. Clear, students? So at this point, so as to make the body execute the vertical circle loop, T must be greater than mg cos theta, because net force must be acting in the radially inward direction. It will be able to execute vertical circle loop only if net force experienced by the body is in the radially inward direction. That should provide the body the necessary centripetal force, right? So let's try to construct the equation. At point A, what will be the equation? T is greater than mg cos theta. So net force in the radially inward direction is T minus mg cos theta. And this net force acting in the radially inward direction will provide the body the necessary centripetal force. So its mass is m. At this instant the velocity is v. So centripetal force is mv square by r. R is the radius, which is the length of the string under consideration. Right? So what we do is, it can be rearranged like m by r. It can be taken as common v square. Over here it will get plus gr cos theta. Simply rearrange the terms. Right? This term on going on the right hand side, it will become plus mg cos theta. Take m by r as common. So what do we get is m by r, v square plus gr cos theta. Clear, students? Now cos theta. From the diagram, the value of cos theta can be easily evaluated. What to do is, draw this line. Students, this is h. This is h. And the radius, which is the length of the string, is r. Right? So what about this distance? It will be equal to r minus h. Isn't it? This is r minus h. So this being a right angled triangle, we can easily find out the value of cos theta. Cos theta from here, it can be easily judged. Cos theta, it is equal to base over hypotenuse, that is r minus h divided by r. Am I clear? So let's come back to this equation. So we get T is equal to m by r v square plus gr, and cos theta is r minus h divided by r. So students, the expression for the tension is m by r v square plus g r minus h. R get cancelled. So put this as equation number 2. So this is the expression for the tension in the string. Now students, what we do is, let's substitute this value of v square over here, right? So what we get is, t, it will be equal to m by r. In place of v square from equation 1, we can write vl square minus 2gh plus g r minus h. Actually, let's put this as equation number 2. Clear students? So this is the expression for the tension at any point during the execution of the vertical circular loop by this body of mass m. Now let's find out the expression for the tension in the string at the lowest point and at the highest point. So let's find out the expression for the tension at the lowest point. Let's find out the expression for the tension at the lowest point. What to do is, at the lowest points, students, suppose tension in the string be represented by TL. So this is the lowest point, the tension in the string, suppose this is TL. Tension, as you are aware, it's a force which acts along the length of the string towards the point of suspension, right? So T equals to TL at the lowest point. And what is H? At the lowest point, what is the value of H? Over here, it will be 0. Therefore, students, from equation 1, or rather from equation 2, let's substitute this value over here. In place of T, we will write TL, isn't it? It is equal to m by r VL square. H is 0, so this term gets eliminated, plus 2 plus GR. H is 0, so we will be left with plus GR. Put this as equation number 3. So students, this is the expression for the tension in the string at the lowest point. TL is given by m by r inside bracket VL square plus GR. Similarly, let's try to find out the expression for the tension at the highest point. Tension at the highest point. Now when the body is at this position, the tension will act again along the length of the string towards the point of suspension. So this is the tension at the highest point, right? So at the highest point, T would be replaced by TH, and H, when the body moves from the lowest point to the highest point, then the height which will be gained by the body during the process would be equal to twice of the radius. It is the diameter, so it will be equal to twice the radius of the vertical circular loop, right? So let's substitute these values over here. What we get is TH is equal to m by r VL square minus 2G. In place of H, we are supposed to write 2R plus G R minus H. R minus, in place of H, we are supposed to write 2R. Clear students? So let's evaluate it further. So m by r VL square minus 4GR minus GR. So that will give us the expression for the tension in the string at the highest point. It is m by r VL square minus 5GR. So students, this is the expression for the tension in the string at the highest point, right? Now there's a very important conclusion basically. We will try to find out the difference in the tension at the lowest and the highest point, right? So let's find TL minus TH. What is this? It is basically the difference in the tension at the lowest point and the highest point. Obviously at the lowest point the tension is maximum, while at the highest point the body is almost in the state of free fall. So at the highest point the tension in the string is minimum. So let's find out the difference in the tension in the string at the lowest and the highest point. So for that, what to do is third minus 4. So in the left hand side we will get TL minus TH, and on the right hand side what we get is M by R VL square plus GR minus subtraction, so the sign will get changed, minus VL square minus plus 5GR, isn't it? So what we get is VL square minus VL square get cancelled, so 6GR, RR get cancelled, so we get 6 times mg. Mg is equal to the weight of the body, so it is equal to 6 times the weight of the body under consideration. 6 times the weight of the body under consideration. So students, this is a very important conclusion. So what we have mathematically verified is the tension obviously at the lowest point of the string would be maximum, and at the highest point the tension in the string would be minimum, and the difference in the tension in the string at the lowest and the highest point is equal to 6 times the weight of the body. That is what we have derived. TL minus TH is equal to 6 times the weight of the body under consideration. So students, these are the expressions which we have derived, right? Tension at the lowest point is TL equals to M by R VL square plus GR, while the tension at the highest point is TH equals to M by R VL square minus 5GR. And also students, we have proved that the difference in the tension at the lowest and the highest point is equal to 6 times the weight of the body under consideration, right? Now, let's find out the expression for the minimum velocity with which the body needs to be projected at the lowest point, right? For that, we need to be aware of a certain fact that in order that the string doesn't slacken, so that the string do not slacken even at the highest point. That is, it always remains taut. The tension at the highest point must be positive. That is, mathematically, the tension in the string at the highest point must have some non-zero finite value. So, tension at the highest point must be greater than 0. So, we can make use of this fact so as to find out the expression for the minimum velocity which needs to be imparted to the body at the lowest point, right? So, let's substitute the value of TH over here. So, what do you get? M by R VL square minus 5GR, it is greater than 0. That is, obviously M by R can't be 0. That is, therefore, what we conclude is VL square minus 5GR is greater than 0, which implies that VL is greater than square root of 5GR, right? So, using inequality sign, we can safely conclude that the minimum velocity which is to be imparted to the body at the lowest point so as to make it execute the vertical circular loop is square root of 5GR. This is the minimum velocity. So I made use of this inequality sign, right? So square root of 5GR. This is a very important result which you need to remember. We have derived it over here mathematically, right? Now let's find out the expression for the velocity at the highest point. So for that, what we do is we can make use of this expression. From first, what we get is V square is equal to VL square minus 2GH, isn't it? Now let's substitute the value of VL over here. And also at the highest point, students, at the highest point, V, the velocity, it will be replaced by VH, and H, as we are aware, as the body moves from the lowest to the highest point, it will gain height equal to the diameter, which is 2r. So let's substitute this value over here. What we get is, in place of V, we can write VH. In place of VL square, we can write 5gr. This is obviously the minimum velocity which is required. VL is square root of 5gr, to VL square root get cancelled, so we'll be left with this. Minus twice g, and in place of h we'll write 2r. So this will give us 5gr minus 4gr, that will give us gr. So students, the velocity at the highest point is square root of gr. So this is the expression for the velocity at the highest point. Now, you should be easily convinced why this body doesn't fall in the downward direction. Because at the highest point, its velocity is not zero. In case it was zero, it would have dropped freely and followed a straight path, downward direction. But since it possesses this velocity, root gr, therefore it moves forward and is able to execute this vertical circular loop. Right? So these are some very, very important results which you need to remember. First is the expression for the velocity at any arbitrary point, then the expression for the tension at any arbitrary point, then we have found the expression for the tension in the string at the lowest point, the expression for the tension in the string at the highest point, then we have determined the minimum velocity of projection at the lowest point, and that is square root of 5gr. And at the highest point of the vertical circular loop, the velocity which the body possesses, square root of gr. So these are all very, very important results, right? There are various applications as well. Suppose a bucket which is filled with some water, if it is made to execute a vertical circular loop, and at the lowest point, if it is imparted velocity root 5gr, greater than that velocity, then at the highest point, when the bucket gets inverted, then also water will not spill out from that bucket. It is because at the highest point, it will have velocity of root gr. So it will execute the vertical circular loop without the water spilling out at the highest point. The weight of the water along with the bucket will provide the entire system the necessary centripetal force. So there are other various applications of this as well, which we will discuss while doing numericals based on this topic. Right? So that's it for this particular session, students. Do join me in my next lecture then. Till then, bye-bye, and do take very good care of yourself. Thank you.